Welcome to Spring LIB.
So we're told that an airplane propeller has a tip-to-tip length of 2.08 meters, and it weighs 117 kilograms. And it applies, initially at least, it applies a torque of 1,950 newton meters. The engine does to the propeller. Now, we're going to assume that the propeller is just a rigid bar rotating about its center. So the mass moment for that is 1/12 ml squared. And so we know that the initial torque equals the mass moment times the initial acceleration. So the initial acceleration is 12 times the initial torque over ml squared. Plugging everything in, we get that is 46.2 radians per second. Now, we're asked to, what is their angular speed after 5 revolutions? Well, we can use our kinematic relationship that the final velocity squared, the final angular velocity squared is the initial angular velocity squared plus 2 times the acceleration and over the angle that acceleration acted. And again, we're assuming that this is a constant acceleration. Initial speed we were told was 0. So the final speed is the square root of 2 times alpha naught times the change in angle. The change in angle we're told is 5 revolutions, but that's 10 pi radians. So plugging everything into here, we get the final angular velocity is 53.9 radians per second. And then we'll ask how much work is done by the engine during this first 5 revolutions. Well, the work is just the torque times the angle of rotation. And again, assuming this torque is always constant, I guess we call that T naught. Assuming that we have a constant torque over the whole range, that's simply just 1,950 times the angle, which is 10 pi, or that winds up being 61.3 kilojoules. Now they ask, what is the average power output during the first 5 revolutions? Well, we need to figure out, to get the power, average power, we need to figure out how long it took to get up to this speed here, or how long it took to go through 5 revolutions. So delta t equals the change in angular velocity divided by the angular acceleration. And again, this is assumed to be constant. This is 0, so we wind up with 1.17 seconds. So it took 1.17 seconds to go through 5 revolutions. I'm not sure if I did 5 or 6 there, but anyway. So now that we know the time it took, we can say, well, here we have the work that was produced, or the work that was put into the propeller over that time. So divided by the time gives us an average power. And that average power winds up being 52.4 kilowatts. They then ask us at the instant, what is the instantaneous power after it is turned through 5 revolutions? So that means that we have the instantaneous power is the torque, which we know, I assume it's still this value, and the final velocity, which we know. So that's just that. And plugging all those in, we get 105 kilowatts. So we can see it's almost about double what the average is. And in fact, I think it is exactly double. And because basically the power starts off as 0 because there's no angular velocity, right? And then it ramps up. We're assuming the angular velocity grows linearly. And so the average is going to be half. So again, I rounded this off. So the average is actually half of the power at the end, because obviously the power was going up as the angular velocity was going up because the torque was constant.